Is over chapter 10. We want to cover three topics. Number one, how to deal with log forms of equations, to take those and change them to exponential or vice versa to solve for unknowns. The second part will be to learn the laws of logarithms, the three rules. In the third part, we'll learn how to solve equations where we need to use properties of logarithms. So let's begin the tape with this definition that's at the top of page 127 in your textbook that says, if the log of a number to a certain base is equal to x, then we can rewrite that as the base, whatever this number or letter is here, raised to this exponent equals to that number. Now, if you'll go back on page 126 and read the definition of logarithm, you will notice this, and this is what I want to point out. The log of a number is an exponent. Is an exponent. The log of a number is an exponent. Keep that in mind when we get to later on this tape on some of the laws of logarithms. Now, what I want you to do at this point is just to memorize this statement. To be able to take a log statement and change it to an exponential statement. Remembering that the b is what's called the base, so when I use that word, you'll know what I'm talking about. Whatever this number is over here is called the exponent. It is an exponent. And n is the number. Now let's go back and look at this and talk about the definition of logarithm. The log of a number is the exponent that I must raise the base to equal that number. Well, that's what this says. The log of a number is the exponent that I must raise the base to equal that number. That's what this says. The log of a number, 455, is whatever I have to raise a base like 10 to get 455. So this is the exponent, this is the base, this is the number. All right, let's look now at the examples through your notes. We'll start with example 1 and see how we can work this. All right, we have the log of 36 to base 6 is equal to what? Changing to exponential form. It's the base to this exponent equals the number. The log of the number is what exponent must we raise the base to get that number. So we have base to this exponent is equal to that number. And we have 6x is equal to 36. Now at this point, what I want you to understand is this. I'm going to show you a method to use that deals with the harder type of problems. This one, everybody can see that, well, that's got to be a 2. 6 squared is 36, so that's got to be a 2. But watch this method. Here's what you do. When the unknown is up here in the power, then you get these bases, or you change this over here so it has a base and a power, and you get these bases to be the same. Base 6 to the power x, then I can change 36 to 6 squared. Now what this means in these problems, and most problems you get on your homework and on test, is you need to know the numbers like 2, 3, 4, 5, 6, and 7 to the powers up through 4, 5. Like 6 to the third power, you need to know that. 7 to the third power, 5 up to about the fourth or fifth power, 4 up to the fourth or fifth power, 3 and 2 up to quite a few powers, 6 and 7 and 8 power. If you'll know that 36 is 6 to the second power, then it will help you go through this process. But let me go back and repeat. What I'm saying is, when you have an unknown in the power up here, you get these bases to be the same. Then you simply say, look, if this is equal, if this quantity over here is equal to this quantity, and these numbers are the same, then that has to be the same. So this has to equal this. And so we can say, therefore, x is equal to 2. Now, let's check our work. X is equal to 2. Go back up here. What? The log of 36 is what power must we raise the base to get 36? And 2 works. So the log of 36 is 2. All right, example 2. The log of 81 base 3 is equal to what? All right, we change it from here to exponential form. It is base raised to the exponent is equal to the number. And again, if you have the unknown on the top, then you get these to be the same. 81 is 3 to the 4th power. Now, if you don't know that, you're going to have to experiment. You just try 2 and take 2 times 2 times 2 times 2 times 2 and see if you ever get 81. If that doesn't work, then you try 3 times 3 times 3 times 3 and keep going. If that works, you got it. If it doesn't, then you try 4 times 4 times 4, and then if that doesn't work, if you don't know these, you're just going to have to trial and error. Again, though, you get these bases to be the same. And then when these are the same, therefore this has to be equal. Therefore x is equal to 4. Let's check it. The log of 81 is what power must I raise 3 to get 81? And 4 works. Okay, let's go to example 3. The log of 1 base 8 is equal to what? Well, 8 raised to the power, the exponent, is equal to 1. Change this. This is an extremely important concept for you to know in calculus and a lot of other math courses. Not these steps below this so much, but knowing how to change from log to exponential or vice versa. All right, let's continue here. X to the 8 to the x power is equal to 1. Now here at this point you need to remember any number to the 0 power is 1. Any number except 0. Okay. 8 to the 0 power is 1. So I can just make this base 8. I could have said 9 to the 0, 8 to the 0, 7 to the 0, any number. But I'll make it 8 to the 0 because 8 and 8, we want these to be the same. All right, so now I have the same base, therefore the exponents are equal, therefore x is equal to 0. Let's go back and check that. 8 to what power equals 1? Well, 8 to the 0 power is equal to 1, so that checks. All right, example 4. The log of 9 to the base 27 is equal to x. What is the log of 9 base 27? What is it? We don't know, so we put an unknown here, and then we change it. It will then be 27 to the x power equals 9. Now we have a problem of getting these to be the same base. Well, 27 is not a square or a cube or something like that of 9. So what we'll do is take both of these and get them to the same base. So noticing 27 is 3 cubed and 9 is 3 squared. Now remembering your rules about exponents, a number raised to a power is multiplied, this times that. So that'll be 3 to the 3x, 3 times x equals 3 squared. Now, since we have the bases the same, then we say 3x equals 2. Solving for x, we divide by 3, and x is equal to 2/3. Now, at this point, let's check this one and learn some things also. Here we have 27 to the 2/3 power. 27 to the 2/3 power is equal to 9. Is this true? When you have a fractional power, what you do is take the root, this root of the number. What is the cube root of 27? In other words, what multiplied 3 times gives us 27? Well, that's 3. So the cube root of 27 is 3. Raised to this power, in other words, squared, is 9, and it checks. Now don't forget that also. That's another thing you need to know about powers all through other math courses, is if you have a number to a fractional power, it's this root of the number raised to that power. And it's better to do it that way than raise it to the power and then take the root of it. If 27 squared, how many of you know what that number is? And then after you get that large number, what is the cube root of it? So it's easier most of the time, if possible, if you know the root of the number, to take it first and then raise it to that power. All right, let's go to example 5. And on these problems now, I'm getting to problems where I'm trying to teach you powers and laws that you're supposed to already know. But we will take time to review them and go over them. The concept in this chapter is simply to be able to take this step and get to this step. From there on, it's algebra work. All right? The log of 9 to the base 1/9 is equal to what? So we say 1/9 to the power is equal to 9. Now we must get to be the same base. All right, now what I will do then is take this 9 right here and using idea of negative powers, 9 to the minus 1 is 1 over 9, and when you invert and multiply, you get 9. That's one way of doing it. Another way of doing it is to look at this as 9 to the minus 1 raised to the minus 1 power. Minus 1 times minus 1 is a plus 1, so that's the same answer. Now, what is 9 to the minus 1 power? This is what you're supposed to know. A number to a negative power is 1 over that number to the positive of that power. Let me say it again. 9 to the minus 4 power is 1 over 9 to the plus 4. So by that process, I have taken now and got these to have the same base. Therefore, this is equal to this. So x is equal to minus 1. Now, let's go back and check that. Okay, at this point, let's check that. This says we have 1/9 to the minus 1 power is equal to 9. Now again, some things you should know. If I have a fraction to a negative power, then all you do is flip it over and change it to the positive power, and it checks out. All right, let's go to example 6. If you do not understand some of this, then you need to see the teacher, and also you should go back and study, find an algebra book and do some studying on it. Example 6. The log of 1/2 to the base 32 is equal to x. What we're saying then, 32 to what power is equal to 1/2? Here again we've got to do some getting the bases the same. 32 is the same as 2 to the 5th power. Okay, and remembering from the other example, we could have put this in parentheses and then removed the parentheses 5 times x. Over here, 1/2 is the same thing as 2 to the minus 1 power. Now you need to learn this. If you don't understand these minus powers, again, you better learn them somewhere, because you're going to have to deal with negative powers to deal with quite a few problems in other math courses also. All right. Then that changed now to the same base, and therefore 5x is equal to a minus 1. Since 5x is equal to minus 1, dividing both sides by 5, we get the answer x is equal to the minus 1/5. Now, let's go back and check that. X to the minus 1/5. Let's just see how that works. I'm doing this as also a teaching device. 32 to the minus 1/5. All right. The fifth root of 32 is 2 to the minus 1 power. Remember, the denominator, you take the root of the number, and then whatever you get, you raise it to that power. Now, what is 2 to the minus 1? It's 1/2. So it checks out. All right, let's continue to example 7. Example 7 says the log of 1 over 81 to the base b is equal to minus 4. Now here the unknown is over here. Well, it doesn't make a difference whether the unknown is here, here, or here. What we'll do is take this base to this exponent is equal to this number. So b to the minus 4 is equal to 1 over 81. All right, now in this step, our unknown is here, not up here as a power. So what we do now is try to get the powers the same. If we can get these the same, then our answer is here. All right, So let's see what we can do. 81 is the same thing as 3 to the 4th power. So that would then be 3 to the minus 4th power, because we multiply powers here. So we now have b to the minus 4 is equal to 3 to the minus 4. If these powers are equal, then this must be the same thing. Therefore, b is equal to 3. Now here's the other trick that I was telling you about, is now if your unknown is down here, then the rule is to get the powers the same. To get the powers the same. So looking down now about 4 lines, we notice we have through algebra gotten these powers to be the same, therefore the unknown is here. Now again, let me break in and say this. There are some problems many times that you do that you can just see what the answer is. What I'm trying to show you is a rule, a method that will work for any and all cases, because there's some that will get more complicated and you can't just see the answer. But if you'll go through these two procedures, either get both these to be the same and your answer is here, or you get these to be the same and your answer is up here. That process will work any and all problems like this. All right, let's go now to the next example. Example 8. We have the log of a number to the base 32 is equal to 4/5. Here in this case, we're looking for this one. So, to make a difference, we still use the same rule. It's the base to the exponent is equal to the number. So 32 to the 4/5 power is equal to n. All right, here again we have the same lesson. The 5th root of 32 is 2. Raised to the 4th power is 16. I just made an extra step out of this. Doesn't mean you have to on your work. But the 5th root of 32, whatever that is, which is 2, then you raise it to this power, and then you work it out. Okay, example 9. Example 9 says the log of number base 6 is equal to minus 2. This is just another example using negative powers. Therefore, this is 6 to the exponent minus 2 is equal to the number. And this is 6 to the minus 2, which is 1 over 6 squared. In other words, the rule is a number to a negative power is 1 over that number to a positive power. And then 6 squared is 36, and so you have n is equal to 1 over 36. All right, let's go to example 10. Example 10 says base, a number here, a base raised to a power, all this is the exponent, is equal to a number, equal to something out here. Now you got to watch this on some of your homework. This x now is no longer that x that we've been used to dealing with. This simply says 10 raised to some power is an unknown. Now that's base and that's exponent, so this must be the number. That's a base, exponent, this must be the number. So a way of doing this is to say then that let's change it from exponential form to the log form. Let's go backwards. We're going from exponential form to log form. So to do that, think with me, I write down log. Now what goes here? Base. What goes here? Number. What goes over here? Exponent. So if I want to take an exponential equation and change it to a log equation, then I say that goes here, that's the number, it goes here, that's the power, the exponent, it goes here. Now, look what we have. If the log base 10 of this is equal to log base 10 of this, then these must be equal. So x is equal to 2. Well, if you look back at the top of page 127, underneath those two formulas that I asked you to memorize before, you will notice this kind of statement. It says that if you have a base raised to the exponent log of something to the same base, if these are the equal right here, the same thing, then the answer is 2. So let's look at the next example. Using that concept, e to the log base e, 5 equals to what? Equals to 5. Now, this is a nice thing in certain places in math, that you can say something like that. Base e raised to the power log of 5 base e is simply 5. That's equal to 5. We just get to replace all that and put 5 down. Okay? You might want to know that and use it sometime. So there it is. These two are not, example 11, example 10, are not that big a deal. It's nice to know, and it would be nice if you remember that. All right, now let's look at the last 3 statements that we have on this particular part of the tape of learning the exponential and log. And these are 3 things that you must memorize. You just memorize them. Now, I don't want you to have to go back and prove them every time. You just memorize them. Let's take the first one. The log of 1 is always 0. The log of 1 is always 0. Why? What power do we, or this 0, we put to this base to equal this? So this base, no matter what it is, if that's a 2, if that's a 10, if it's an 8, a 5, whatever, anything raised to the 0 power, that's exponent, is equal to 1. So the log of 1 is 0. Just memorize it. Don't waste time to trying to reason why. I've shown you why. You just memorize. The log of 1 is equal to 0. All right, the next one. The log of 0 is not possible. The log of 0 is not possible. Now here's the reason, but you just memorize it. Also, what base, the base raised to what power is equal to 0? Now these bases that we're dealing with in this chapter and almost all problems you'll deal with in the first 2 or 3 years of mathematics, the bases of logarithms are always a positive, non-zero number. In other words, they're always numbers greater than 0 in any application. When you get into higher mathematics, you can deal with negative bases. But let's stay with here, and that's what we're saying these rules about. Now, if that's a positive number raised to what power equals 0? Well, there's no way that you can take any number, positive number, and multiply it by itself and get 0. See? So it's impossible to have the log of 0. It's impossible to have a power to this base to equal 0. So you memorize. Log of 0 is not possible, and you just memorize it. You hear? Okay, next one. The log of minus 10. The log of a minus number is equal to not possible. Again, why? If we have a base raised to what power is equal to a minus number? Well, you remember I just got through saying in this course and most other courses you deal with, that base is a positive number. How can you take a positive number and multiply it by itself and get a negative number? So the log of a minus number in this course is not possible. The only way that this can happen is if you have a negative base, and we will not deal with those in this course, nor your calculus courses or things like that either. All right, so here are 3 concepts that you need to remember. The log of 1 is 0, the log of 0 is not possible, and the log of a minus number is not possible. Now don't get this last one mixed up. The log of a minus number, I'm not saying exponent. The exponents can be minuses. We have dealt with those in other problems. But the number, the n, cannot be a negative number. This portion of the tape is dealing with the 3 laws of logarithms. So let's look at those. The first law says that the log of a product, now don't get too wrapped up with the m and m. What I'm saying, the log of a product, some object times some object, is equal to the log of m plus the log of n. If I have the log of a product, that's equal to log plus log. Now, if I have 3 or more or 4 or more, it's the same rule. If I have the log of 4 things, then it would be log plus log plus log plus log. Right quick, the reason behind this is what? Logarithms, the answer to the log of something is an exponent, and we add exponents. Remembering, if we have 5 to the 4th times 5 to the 6th, that's 5 to the 10th. We add exponents. This is an exponent. The log of a number is an exponent. So it can be broken up into the sum of exponents. And that's the reason that it's that way. You just memorize. The log of a product is log plus log. The log of a division is log minus log. Again, for the rules of powers. When you have a number to a power raised to a number to a power, you subtract powers. I'm sorry, divide it. You have number power divided by number power. When you divide, you subtract powers. And then the last law here is the log of a number raised to, if the number is raised to the power, now listen closely, that's not if all of this is raised to the power, but the log of this, then you can take that power and move it out in front, and it's times the log of the number. Now, what I want to do at this point is to show some examples with just numbers in them, and X or so, just to learn the laws. Not that these problems are kind that you'll be having to work in other math courses or in trig, but these problems are just to teach the concept of, if it's the log of a product, you can split it up or you can go the other way. If you happen to have a log plus a log, then you can combine this and make it into one single term. If you happen to have a log minus a log, you can combine this into a single term. If you happen to have a number times a log, you can take that number and move it up here to that power. So I want you to memorize these things just like an identity concept. In place of this, you can replace it with that. Or in place of this, you can put it like this. All right, so let's look now at example 12. Example 12 says the log of 35 is equal to the log of 5 plus the log of 7. Now watch what's happening here. I must be able to break this up into a product. I cannot take the log of 37 because 37 you cannot find factors of. You cannot split that number such that it multiplies. So what I'm trying to say is you can only split the log of 35 up into numbers that multiply. We could have 5 and 7, and that's it. There's not any other factors. And so looking at example 12, let's look back at the rule that says the log of 35 is log of 5 plus the log of 7. That's the log of 35. The log of 35 is the log of 5 plus the log of 7. All right, let's look at the next one, example 13. Example 13, we have the log of 10x. This is equal to the log of 10 plus the log of x. Again, product here, 10 times x, so it's 10, and then plus the x. Now, like I said, these problems, I'm just going to throw in some other things that you need to know. What is the log of 10? Well, unless there is something written here, when we use the word log, it will always be understood to be base 10, unless something else is written there. Now you need to remember that throughout this course and other courses. Most calculus books will have log, meaning base 10. If they want another base, which some of them use base E, they will spell it ln. But in here we can be assured that the logs they're talking about are logs, which is base 10. So if it's not written, it's understood to be a 10. All right, log of 10, base 10. Let's go back to the previous part of this tape. what power must I raise 10 to equal 10? 1. So this can be simplified in this case to 1 plus the log of x. Now again, the purpose of this problem is to go back now and let's look at the rule. The log of a product is log plus log. All right, and this is what we have in example 13. The log of a product, 10 times x, is log plus log. All right, example 14. Example 14 is using the log rule of division. I have the log of a division problem, and that's equal then to log minus log. And again, the log of 10 to base 10 is equal to 1. What power must I raise 10 to get equal to 10? Power 1. Again, the purpose of this problem is to show the log of division is log minus log. All right, let's go to example 15. Again, these are just numbers and throwing in some other things that should help you in some of your homework problems. But I want to teach the idea of log. Log of 50 is the same thing as the log of 100 divided by 2. I'm just changing 50 into a different form. And of course, I hope you realize I could change it to several different things, but we will take this. The log of 50 is equal to log of 100 over 2. Now this then can be replaced with the log of 100 minus the log of 2. Division is subtraction. Now what's the log of 100? 10 to what power is equal to 100? Well, 10 squared is equal to 100. So the power I must raise this to is 2. So the log of 100 base 10 is 2. 10 to what power is equal to 100? And so that would be 2. So in place of all this, I can replace it with the single number 2, and then minus the log of 2. Now this problem could have been split up another way. We could have had the log of 5 plus the log of 10. And now the answer becomes the log of 5 plus 1. And that answer is the same as this answer. When you work it all out, you'll end up with the same decimal value either way. All right, let's look at example 16. The log of x squared is equal to 2 log of x. All that's simply saying is I can take, if I have the log of a number raised to a power, I can take that power and move it out in front. And as you work homework and some more of these examples, you'll see why we need to know that concept. There are times when you want to take this and move it out in front. There are other times when you want to take this and move it back in. We do it by the third law of logarithms. All right, number 17 example. We have the log of 1,000 raised to the third power. Now, rather than taking 1,000 raised to the third power, saying 1,000 times 1,000 times 1,000, then taking the log of that, I can move the 3 out in front and then take the log of 1,000. Well, the log of 1,000 is 3. Why? Because 10 raised to what power is equal to 1,000? That answer to that is 3. And so our answer is 9. Well, another way of getting that would have been doing something like this. The log of 10 cubed cubed. And so that's the log of 10 to the 9th power. Moving the 9 out in front, we have the log of 10, and the log of 10 is 1, and we get the same answer. What I'm trying to show is the laws here, not necessarily the arithmetic that's involved. There are several ways of getting the same answer of 9. All right, let's continue with example 18 and show some more concepts. Now, another thinking and another concept of this is if we want to take a complicated situation and simplify it to a shorter method, we can. Log plus log is the same thing as the log of product. So what I'm saying here is we're going to go backwards. We're going to be given the right side of the situation and simplify that back to a single term. So remembering log plus log is multiplication. All right, number 19. The log of pi plus 1/2, all this. Well, the first concept, let's work this inside. The The log of x minus the log of y is the log of x divided by y. Remembering, subtraction is division. Log minus log is log division. Then the next step is to take this number, this is the power, and move it over here to this power. So I'm going to take this power out in front and move it out here. Then the next step is simply trying to make you realize that this is the same thing. Okay? The 1/2 power is the same thing as square root, right? Square root is the second root raised to the first power. So it would be the second root raised to the first power. All right, then I can combine now. This log plus log is log multiplication. All right, let's go to the next example, number 20. Number 20 says 7 log of x minus 1/3 log of y minus 2/7 log of z to 7. Have all that thing where we can simplify it. If all these are logs, if everything along here is a log, then I can simplify that by this method. First of all, I can take this 7 and move it up in here as a power. Then subtraction means division. So I'm going to take this part, which is x to the 7th, and divide it by this part. Well, again, I can take this power right here and move it in here. So I'm dividing by y to the 1/3. Division, again, simply says keep dividing. So this goes on the bottom. And again, I can take this power out in front and move it inside here, and those divide out, and we have z squared. Now, if you don't see all that arithmetic moving this in, you need to study this some more. But what I'm saying is this: we can take these powers and move them, these numbers in front of the log and move them in as powers. Number in front of the log, move them in as powers. Number in front of the log, move them in as powers. Then subtraction means division, subtraction, division. And another way of writing this is this. It doesn't make a difference really which way. I just want to show you that log of 1/3 power is the cube root to the first power. All right, example 21. We have this big, long, complicated mess. And here's log plus log plus log minus. So it says this times this times this divided by this. Okay, logs added or multiplied, log subtracted, division. Then moving this power in, bringing this 1/2 over here, is the square root of all that. And there you have Hero's number. All right, let's now look at some other examples. Let's now look at example 22. Now, here we have a big, complicated arithmetic problem. 1.479 raised to the 5th power times 5826. And that's just a whole lot of headache, work, pencil and paper. Now, people nowadays with calculators, this is no big deal. But let's consider a usefulness of the laws of logarithms. Back when we did not have calculators and we had to do a problem like this, this would mean we would have to take 1.479 and multiply it by itself and multiply it and multiply it and multiply it. And the idea of logarithms simplifies to all we have to do is to is to add and multiply. For instance, this then, taking the log of both sides, if I take the log of both sides, I now have the log of this is equal to the log of what I want the answer to be. Okay. Now, what is this over here? The log of a number raised to a power times. I can take this down here, and it's times the log of 1.479 plus, this is multiplied, the log of 582. Looking at the log of 1479, that's 0.1700. Now, at this point, let me break in to the concept of this problem and say, if you have a calculator, then at this point you just punch that button. You hit 1.479 and you go hit the LOG button on your calculator. Don't hit the LN. Hit the LOG button and you should get, and it really comes out to be 169999, but I just rounded off to 0.1700. You find the log of 5826, hit the log button, and you get 3.7691. And then you multiply by 5, and then you add this together, and now you have the log of x is equal to that. Now, from this step, we will change back now. This log is base 10. 10, this base, to that power is equal to x. And then you can use your calculator and say 10, use the y to the x power button, and take 10 and then hit the yx button, and then put 4.6189 and hit the equal button, and you got the answer. Now, I realize that I'm telling you how to use different buttons on the calculator, and you're coming up with the same thing. You could have come up quicker. What I would like for you to see in this problem is back before, or if you don't have a calculator. If you did not have a calculator and you got to work some kind of complicated mess like this, then what you do is these steps right here, and you look in the back of the book and look up the log, the table 2 back there. Now, we've used table 1 for the angles, but for logarithms is table 2, and you can look back there and find these logs and come up with this. Now, if you don't know how to use the tables, then you need to check with the teacher, or possibly there is a tape on this. The part 2 tape of chapter 10 will cover using the tables for logarithms. All right, let's go to the next example then and show again what the purpose of logarithms, one of the purposes of logarithms, is all about. Let's take, we have the 7th root of 428.41. Until calculators were developed, the only way that you could find the 7th root of a number like this was to go through logarithms. So, look how simple it is with logarithms. If I take the log of both sides, it's like squaring both sides or multiplying both sides of the same thing. I'm going to take the log of both sides. Then this becomes 1/7. Remember, the root is the denominator. The power 1 here is the numerator. 1/7 of the log of 428.41 is equal to log of x. Then I look this up in the back of the book, or use your calculator and punch that out, and you get that. Then dividing by 7, I get this. Then I can say 10 to that power is equal to x. Now again, there's a lot more to this, a lot more things I could teach here. For instance, you could go backwards on your calculator. If you put 0.3760 and you hit inverse log, the 2 buttons, hit the INV button and then the LOG button, it will come back and give you the final answer. Okay. The concept, though, is right here. If I have the log of x to base this is equal to this, then it's this base raised to that power is equal to x. And working that out, it comes out to be x equals 2.38. That example is an example of showing that the logarithms was a very useful, and still is if you don't have a calculator, is a very useful concept in dealing with just arithmetic. All right, let's look at one other example and show again how useful logarithms used to be before the calculator became so inexpensive that anybody could buy one. If we have a big old complicated mess like this, this would take almost forever, most of us, to work. Whereas it's simply the log plus the log times 4 minus the log to the 1/3 of that. So we have the log of 876.22 plus 4 times the log of this minus 1/3 the log of 3648 is equal to log of x. And we look up the log of that. We look up the log of this, multiply it by 4. We look up the log of this, multiply it by 1/3. And then subtract this from these 2 additions, and it comes out to be 6.2564. Again, you can use your inverse log button and you get the answer. Or you can come back and say 10 to this power is equal to x. So here are some examples. These 3 are just put in the notes to show you why logarithms used to be important in terms of just dealing with arithmetic. All right, now let's go to the next part of the tape and the final section of this chapter, and that is how can you solve logarithmic equations. And there are 2 types that I want to show you. These are the first type. This example 25 and 26 I'm going to show, and then show you some more examples. If I have an equation that has a bunch of logs in it, logs plus logs equals logs plus logs, then I can do this by coming back and saying, hey, I got a log plus a log. That's combined. Log plus log is log of multiplication. And I just leave this one alone. Now, I have log equals the log. If that's true, then this must equal that. So then I can just say, hey, this then must be equal to 50. If the log of this object is equal to log of this object, then these objects must be equal for this equality to be true. So then I work this out, and the algebra is the rest of it. Multiplying this together, first times the first is plus 6x minus 9x. That's a minus 3x. This one times this one's a minus x squared, and this one times this one's a 54. Getting everything to one side, moving this across plus x squared, moving this across plus 3x, moving this across gives us a minus 4. Factoring, we get x equal to a minus 4 and 1. Now, never forget you need to check these answers. Go back and check these in the original problem. If I put a minus 4 up here, I get 6 minus a minus 4, that's 10. If I put a minus 4 here, plus 9, that's 5. Log of 10 plus a log of 5, that is a log of 50. So this one checks. Now if I put a 1 in there, I get 6 minus 1. That's the log of 5. If I put a 1 here, I get 10. Log of 5 plus a log of 10, that's log of 50. That's good, that checks. So both of these check out. All right, so let's go to the next example. Example 26. Here we have 2 times the log of 1 minus x equals the log of x plus 11 plus the log of 2. Now here I will move this 2 up here as a power. I will combine these two. Log plus log can be combined into single log, and it's multiplication. 2 times this. Now again, I have an equality where log is equal to log, and therefore that means this must equal this. Working this out, 1 minus x squared is 1 minus 2x plus x squared. Multiplying this out, 2x plus 22. That's just algebra from here on. Moving everything to the left side, I have a plus x squared. Moving this across, I'll have a minus 4x now. Moving this across, I'll have a minus 21. Factoring that, and then setting each factor equal to 0 and solving for x, I have x equals 7 and a minus 3. Well, we better check it. Putting a 7 back in the original problem, I have 1 minus 7, that's a minus 6. What is the log of a minus number? It does not exist. So 7 is not a solution to this problem. And checking the minus 3, it will work. Back up here in the original problem, you have 1 minus a minus 3, that would make that a 4. And then putting a minus 3 over here would make this 8. Now, log of 8 plus the log of 2 would be the log of 16. The log of 4, this 2 moved in as a power, would make it 16. So the minus 3 does work. Now looking at example 27 and 28, the next one, what I want to point out by these two, the difference between these two and the last two. This has log equals, and then we have just a number here. It's not all logarithms in the equation. What do we do when we have a number, or maybe more than one number here, setting with logarithms? The concept then is to get all the logarithms on one side of the equation. Get all the logarithms on one side of the equation. So moving this log across will be a minus log of x minus 1 equals to 1. Then you combine these logarithms on this side. So log minus log would be the logarithm of 7x plus 2 divided by, minus is division, x minus 1. Now, at this point, we cannot say, well, this is equal to that. No, this is log of something equals to just a number. We don't have log on both sides. So now what we do is change from log form to exponential. This is base 10, so it's 10 raised to this power is equal to the number. Now listen to me. What I said, the difference between 27 and 28, if you look back at 25 and 26, you have all logarithms everywhere. And so you just get this combined on this side and this combined on this side, and you set them equal to each other and go work. This is a different concept. When you have a constant involved in it, then you get all the logs on one side equal to that constant, and then you combine the logs. The logs combined are division, therefore, because of subtraction. And then you change from log form to exponential form and then work it. So 10 to the first power is equal to this. Then working this from the algebra the rest of the way, we cross multiply x minus 1 times the 10. 10 times x, 10 times minus 1 equals 7x plus 2. Getting the x's on one side, the numbers on the other side, you end up with x equals 4. Now go back and check that, of course, in your original problem, see if it works, and it does. All right, let's look at example 28, and again look at the concept involved in these. Here we have a logarithm, we have a constant, logarithms. So this concept is we get all the logs on one side by themselves equal to the constant. Then combining the logarithms. This is plus, so that's multiplication. Well, this is 2 times the log of 5. I can move that 2 up here as a power, and that would be 5 squared, which would be 25. So the log here is 25 times this, minus, which means divided by 7, equals to 2. And again, at this point, we do not have log on both sides, so we can't set these equal. We have to then say 10 raised to this power is equal to this. And then solving this, cross multiplying. 10 squared is 100, times 7 is 700, equals to this, doing your algebra, and you come out with x equals 17. All right, let's look now at example 29. Now, example 29 is dealing now with the last type of problem that you have to deal with sometimes using logarithms, and that is, what happens when you have an equation such that it's some number raised to a power is equal to this? In fact, this problem is almost impossible to work even with a calculator. It has to end up being a trial and error situation. So this one just must be done with logarithms. Now what we do then is take the log of both sides. Taking the log of both sides, we have the log of this is equal to the log of the 2500. Now let's move this x power down. We move the power down in front, and now we're just solving. X's are unknown, and this is a number, and this is a number. So x then is this divided by this. In other words, just like if I had 5x is equal to 10, then x would be equal to 10 divided by 5. We're doing the same concept. We're dividing this then into this. Now, caution. The log of 2500 divided by the log of 2.884. That is not a division problem. For a division problem, it must be the log of number divided by number. This is a different situation, and why I'm trying to put that caution in there, too many students make that mistake. There is a difference here. This is log of a number, all divided by a log of a number. So you just have to go look this up, use your calculator, find it to be 3.39794. Look this up, which is 0.4600. Then you divide this out, and you get 7.39. All right, let's look at the next example, number 30. Here we have the same concept. I'm just using different numbers here, but the concept is this. We've got to take the log of both sides. We take the log of this and the log of this. In taking the log of this, we move this power out in front. And so we have x times this is equal to this. And so x is equal to this divided by the coefficient of x. So again, we have x equal log of 0.01439 divided by the log of 2.884. Now this time the log of 0.01439 is a minus 1.8419. divided by 0.466, and that divides out to be a minus 4. Okay, last example. We have 0.001995 to the x power is equal to 0.02378. Again, we take the log of both sides, and moving the power out in front, we have x log of 0.001995 is equal to the log of this number. So x is the log of this divided by this. And we have a log of something all divided by the log of something, so we have to look that up, go look that up, then divide it out, and we come out with x equals 0.6014. So the kind of problems that we're dealing with then is to learn how to solve equations here where we can't do it any other way, where we have an unknown in the power instead of down in here. When we have it up here, then we need to take the log of both sides. The other type of problem is where we have equations that have logs in them. How do we handle those? Equations with logs in them, then we have to use this combination method, combining the logarithms into a single log. Or, if we have everything that's log, we combine these logs on this side of the equal and combine these, and then set that equal to 0. So the purpose of this chapter is to be able to take a logarithm form and change it to an exponential form, or vice versa, and the other purpose then is to work solving equations that have logarithms in them, or solving equations where you have to take the log of both sides and then solve them. This chapter and these problems that I've pointed out are extremely important to you if you're going to take calculus. You need to learn these three concepts. Number one, again, let me repeat it, is being able to take a log form and change it to exponential. That's the beginning of this tape. Number two, knowing the laws of logarithms. The log of a product is sum, log plus log. The logarithm of a division is subtraction. And the log of a number raised to a power is that power times the log. And then the last thing is how to work equations using logarithms.